Hi Chemistry 20s. Today we're going to be doing a lesson on section 1.5 in the textbook on ionic compounds. And so you need your notes and you need your data book to follow along today. Throughout this lesson, we are going to be talking about what an ionic compound is, some of the properties, and also how to name and write the chemical formulas for ionic compounds. So let's get into it. Ionic compounds, as it has in the name, has the word ion in it, which means that we're dealing with ions which have charges that we're going to need to balance. And the way that we end up forming ions is because of that gain and loss of electrons. So our definition of an ion compound is it's formed when a metal atom collides with a non-metal atom, causing it to lose the electrons. So ionic compounds are formed when metal atoms collide with non-metal atoms, which results in it losing electrons to the non-metal. Okay, and when we have those ions that have formed, it's the opposite charges that attract to each other, and that's actually what an ionic bond is. It's that attraction between the cation and the anion. So we're going to write the opposite charged ions are attracted to each other, forming an ionic bond. So the example here, we have magnesium and oxygen, similar to our combustion of magnesium lab that we did the other day. So these are both drawn out as the atoms. So magnesium has 12 protons, and therefore it has 12 electrons as an atom form. Oxygen has 8 protons, so it has 8 electrons. And the reason why they gain or lose is because they want those full outer valence shells. So when magnesium and oxygen collide, what happens is the magnesium wants to get rid of those 2 electrons in its outer shell. So it's going to transfer them over to oxygen. And as a result, magnesium has lost 2 electrons. So we end up with the magnesium 2 plus, and oxygen has gained 2 electrons. And so we end up with oxygen 2 negative. Okay. And so when we put that together, because magnesium gave up 2 and oxygen gained 2, that's how we come up with the formula MgO, or magnesium oxide, for that compound. And it's the attraction between the cation and the anion that are holding that compound together. Okay, so when we look at some of the properties, we need to know that all ionic compounds are solid at room temperature. Solid at SATP, which are just standard ambient temperature and pressure. Okay, and they form a structure called a 3D crystal lattice. So that's what we're seeing in these diagrams here. So because they like to be surrounded with the oppositely charged ion, if we look at the sodium chloride example, and the sodium in the center, it is surrounded on all sides. So it has a negative chloride ion on the top, the bottom, the left, the right. It would be in front and behind. And because of that they want to be surrounded by the opposite ion, they end up creating a cube-like shape. And you can see that represented in the top 3 diagrams. That ionic compounds, that's that crystal lattice shape that they're forming because of those opposite charges. Okay. So they're solid at room temperature. However, when we dissolve them in water, they dissociate and they form a solution that will always conduct electricity to an extent. So in water, they dissociate, which just means to separate. Into their ions. And form conducting solutions. So in the example, when we use a conductivity tester or meter, it is like a little circuit. So you have a battery and you need, in order for the circuit to turn on or an electricity to flow, you need a complete circuit. So at the bottom, when it's sitting in water, if there are no ions, it's like an open switch in a circuit. But if we have ions, so you have positive and negative ions floating around in your solution, what happens is it's able to carry and complete that circuit so that it does conduct electricity. And so all ionic compounds produce ions in the solution, so they're all going to conduct electricity. The last thing I want to note on here is that it's saying when you have a formula, something like sodium chloride, for example, it is just telling us the ratio. So it is saying that there is 1 sodium ion for every 1 chloride ion. So if you actually have a grain of salt, there's many sodiums and many chlorides linked together in that crystal lattice, but it's showing us the ratio. So there's always going to be the same amount of sodium and chloride ions in this case. So it's showing us the ratio, not how many are actually in the grain of salt, for example. Okay. So when we go to do ionic compounds, we have to make sure that the charges for each of the 2 ions are balanced. We need a net charge of 0. So I'm just going to pick some examples, some possible cations and some possible anions for us to take a look at. Okay, so I'm taking their charges off of the periodic table. Potassium has a plus charge, magnesium is a 2+, lithium is a +1, aluminum is 3+, and then some possible anions that we can add together be like chloride ions with a -1, oxygen with a 2-, phosphorus with a 3-, fluoride with a -1. Okay, so when we're putting these compounds together, we need to balance the positive and the negative charges. So for example, if I take potassium and it always wants to give up 1, and I take fluoride, oops, that wants to gain 1, positive 1 and negative 1 balance each other out, and so I just need 1 of each. So when I put those together, we get 1 potassium, 1 fluoride. And of course, we don't write the 1. But if we pick something like magnesium and chloride, now these are no longer balanced. So we have more positive than negative. And so to balance that, we would have to add 1 more chlorine, so that on this side we had a 2 plus and we have a 2 negative from the chlorine. So writing that formula, we have MgCl2 because we needed 2 chlorines. Okay, another example would be aluminum, so 3 plus, combined with oxygen, which is a 2 negative. And so our lowest common multiple for both of these would be 6. So how do I add these up to 6? Is I would need 2 aluminums, so that totals up to 6 positive, and I would need 3 oxygens, because that would add up to negative 6. So when I write the formula then, we have Al2 because we need 2 of them, O3 because we needed 3 oxygens. So you can balance these in your head. You can show your work on the side if you want, something like that. But make sure that when you actually put your final answer, you're not leaving the charges in your formula. So for example, this would be wrong if we wrote Al3 plus 2 and O3 2 negative. Okay, so you do not want to do that. You need to erase the charges if you're going to write them on there. So usually I do that off to the side. I write down what each of their charges are, and then when I put the formula as my final answer, I do not have those charges still on the compound. Okay. Another trick that you might have talked about in Science 10, for example, is the cross kind of multiplication way. So bringing down the charges. So for example, if I had magnesium, which is a 2 plus, and I had bromide, which was a negative 1, you might have been taught that you can bring across the 2 on the bromide and bring the 1 down on the magnesium, which would give me magnesium Br2. So that's kind of a shortcut to help you balancing them. There is some instances where that does not work though. So for example, with magnesium oxide, so magnesium is a 2 plus, oxygen is a 2 negative, but those are already balanced. So if I wrote and brought down those 2's, and I wrote Mg2O2, that's not lowest terms. And so that would actually be wrong, because really I only needed 1 magnesium and 1 oxygen for it to be balanced. So if you're going to use that cross method, just be careful, but it does work for a lot of them. Okay, so always just make sure that you have the lowest terms as your final answer. Okay, so let's talk about naming. Ionic have a couple different types that you can have, and so we're going to start with binary, which just means like there's nothing special about the metal and the non-metal in these. So the naming for this, you put the cation first, and then the anion or the non-metal will end in "ide." So for example, K is potassium, so I'm going to write down the name of potassium, and oxygen would be the oxide, so that it's ending in IDE. Okay, Mg is magnesium. And iodine would become iodide. Al is aluminum. And chlorine would become chloride. So they're all ending in "ide." Okay, take a second and name the next two examples. You can pause the video here. Okay, Na would be sodium, and nitrogen would become nitride. And the last one, Ba, is barium, and phosphorus becomes phosphide. Okay, when we go to write the chemical formulas, again, making sure you balance the charges. So I like to write what the charges are. So for example, I'm looking at barium, 2+, and oxygen is 2-. So those are already balanced. I can just put one of each. So Ba for barium, O for oxygen. And the states for all of these ionic compounds would be solid at those standard conditions, so room temperature, for example. Magnesium is a 2+, sulfide is a 2-. So again, one of each, they're already balanced. Magnesium, sulfide, solid. Okay, so again, pause the video, take a second, try the next 3 examples. Potassium is a positive, iodine is a negative, they're already balanced. So it would be Ki, solid. Rubidium is a +1. Nitride is a 3-. So I'm going to need 3 rubidiums and 1 nitrogen. And the last one, lithium, is a +1. Phosphide is a 3-. So again, we'll need 3 lithiums. So Li, 3, P, solid. Okay, so there's nothing special about these metals and these nonmetals. They just have one charge. They're on the periodic table. Some of the elements or some of the metals on the periodic table have more than one possible charge listed on them. And so these are called multivalent metals. Okay. So metals that can form more than one ion. For example, or that can form more than one ion are called multivalent ions. And so an example here is iron. Iron has 2 possible charges. It could be either Fe3+ or Fe2+. Okay. And so if you look at your periodic table, bring it up here, most of the multivalent are shown in the transition metals. And I said that they exhibit a lot of different properties. And they're a lot more complex. So if you continue into higher levels of chemistry, they'll talk about why they can form different ions. But at this point, we just need to know that they can. Not all the possibilities are listed. These are just some of the most common ones. So you can have other possible charges that are not listed on the periodic table. For reference, the first one that's listed is the most common. And during a reaction, if it doesn't specify which one's formed, you would go with the most common, the first one listed. Okay. So with these, we need to indicate which charge we have, and that means we need to figure out what charge. And we indicate it by using Roman numerals. And so I have them on the side here. They're kind of like lines, right? So 1 is 1, 2 lines is 2, 3 lines. 5 is a V, so 4 is a 1 before 5, kind of a line before the V. And then 6 is V, and then one more. Typically, we don't go past like 7, so as long as we have some of the smaller ones memorized, we don't need to know all the Roman numerals. Okay, so how we figure this out is we actually look at the nonmetal. So I know oxygen always forms a 2 negative. And iron could be 3 plus or 2 plus. So I need to decide which one would balance that out. And to balance it, I would need the 2 plus version. So this would be iron. And in Roman numerals, I would do the 2. So iron 2, oxide. Okay. In the second example, again, oxygen's negative 2. That would give me 6. So this must be the 3 plus on that side. And so this one is iron 3 oxide. Okay, another example. Fluoride is always negative 1, and we have 4 of them. So that means that Sn, which is tin, must be the 4 plus version. So this one would be tin, 4, fluoride. Notice that our nonmetal still ends in "ide," so that doesn't change. The only thing that's different is now we're including the Roman numeral to indicate what charge that ion has, since it has multiple charges. Okay, so pause the video, try the last 3 examples. Okay, fluoride has a negative 1, which means if that has to be 2, this must be the 2 plus. So tin, 2, fluoride. Phosphorus is a 3 negative, so Bi must be the 3 plus. So 3, and then phosphide. And the last one, again, phosphorus is 3 negative. So that would be 15. So this must be 5 plus, so that it's 15 positive on that side. Okay, so those are multivalent metals. So you recognize that you need to add the Roman numerals when you see in your data book you have one of these metals that has more than one possible charge. You need to tell me which one you have. Okay. When we're doing the formula, again, this indicates the charge, not how many you have, which is a common mistake. So if I have chromium, that would be Cr3 plus, sulfide is a 2 negative, and I need to make sure that I'm balancing the charges still. So it would be Cr2, S3 solid. Platinum 4 be Pt 4 plus, oxide's 2 negative, so it would be PtO2 solid. Sorry. And the last one, iron 3, means we have Fe3 plus, oxide is 2 negative, so we would have Fe2O3. Solid. Okay, the last type that we can have is an ionic compound with one of the polyatomic ions. And so on your data book, up here is our chart of polyatomic ions. And you'll notice that a lot of these are very similar. So for example, nitrate versus nitrite, or sulfate versus sulfite. So they're very similar formulas, and because of that, we need to keep the ending. So we don't change anything with the names of the polyatomic ions, because if we changed them to ide, for example, you wouldn't know the difference between nitrate or nitrite. So these ones, if you see more than 2 elements, it must be a polyatomic ion present. And we're going to just write the name down. Okay, so what a polyatomic ion is it's an ion composed of 2 or more elements that are covalently bonded with an overall charge. And most of them are negative. There is one positive ion though, and that's ammonium, being NH4 plus. So most of them are negative, but there's that one positive charge. Okay, and so because they're covalently bonded, that means you can't separate them. You keep them together. They're like a package deal. You never separate them. Okay, and because you have multiple of them, we're going to use brackets if you have more than one polyatomic ion in the formula. So for example, we have sodium, which is Na plus, and hydroxide, which is OH negative. Okay, so I still need to balance them. And they are already balanced, so we would write NaOH. Potassium is a plus. Sulfate, so I go to my chart, look for sulfate, which is SO4 2 negative. Okay, those are balanced. I'm going to need 2 potassiums to balance it. So K2SO4. So notice I have no brackets on those ones because we only needed one of each of those polyatomic ions. And then, sorry, they would both be solids since they're still ionic compounds. Calcium nitrate. So calcium is Ca2 plus and nitrate is NO3 negative. So in this case, I need 2 nitrates. And if we go just like this, and I put the 2 out there, it looks like you have 32 oxygens. And that's not what we want. We need 2 of those packages, or 2 of those NO3s. And that's when we need to put the bracket around it to say that we have 2 of those packages. And the last one, iron 3, that means we have Fe3 plus, and dichromate, Here is Cr2O7, 2 negative. And then balancing those, we would need 2 irons. And then using brackets, we would need 3 of the dichromates. Okay, so a good indicator that you have one of the polyatomic ions and you should be looking at that chart is that often they don't end in "ide." There are a few that do, like hydroxide, for example, but notice sulfate, nitrate, chromate. So if they don't end in "ide", there's a good chance that it's a polyatomic and you should be looking at this chart. As I mentioned, there are a couple that end in "ide", like carbide and cyanide, hydroxide, but I think those are some of the only ones. Peroxide, there's a couple, but if it doesn't end in "ide", chances are you're looking for it in the polyatomic ion chart. Okay, and so those were all review. We are going to add on something called ionic hydrates. So these are new. These are compounds that exist with water within their formula as a solid. So they have water molecules attached. So the example here is CuSO4 and then 5 H2Os. Okay, so in this example, when I look at CuSO4, it has 3 different elements in it. It has copper, and then it has sulfur and oxygen. That is an indicator that the SO4 must be a polyatomic. It is one package together. There's never going to be 3 ions put together. So I would look and I see copper, and I notice that copper is one of those multivalents. It could be 2 plus or 1 plus. So I look at SO4, and I look on the chart. SO4 is over here. It has a 2 negative charge. So 2 negative, which means that our copper must be the 2 plus. So the name for this one would be copper 2 sulfate. And then we get to the hydrate part, the water part. And so to indicate that we have 5 of them, we actually use molecular prefixes. So if you remember these from Science 10, like mono means 1, di is 2, tri is 3, tetra is 4, penta is 5, and so on. So since I have 5 waters, I would say penta for 5. And then it's a hydrate, so pentahydrate, which really means I have 5 waters in that formula. So the whole name altogether would be copper 2 sulfate pentahydrate. On the side here, they have a good picture. So copper 2 sulfate pentahydrate is blue in that form. And then when you heat it up and it loses that water from its formula, it actually turns into a white colored substance. So that's copper sulfate on its own, or copper 2 sulfate on its own. Okay, so it says hydrates decompose at low temperatures to produce water and an associated compound, whatever the ionic compound part was. So here we have another example. So we have iron. Again, iron could be 3 plus or 2 plus. So I look, oxygen's 2 negative. To balance that out, we must have the 3 plus iron. So the name for this one would be iron 3 oxide and then 3 waters. So that would be trihydrate. Okay. So we're adding the hydrate part with the number that we have using the molecular prefixes. Okay, and even these hydrates would be solid at room temperature. So any ionic compound, if it's not put in water, it would be a solid. So this is just a little reminder of that. Ionic compounds are solid at that's supposed to say SATP. And we'll talk about when we use the solubility table later on when we talk about chemical reactions. Okay, so we're just assuming they're all solid at room temperature. So that's the end of the lesson. And so you guys, this is a really important skill to be able to name or write formulas of ionic compounds. And so there are quite a few practice questions in your study guide. It is pages 8 to 11. And so if we look at our study guide, go to page 8. Okay, there's a page on just multivalent metals. So these have more possible charges than just one. And it's asking you to use the most common. So again, that is the first one that's listed on the periodic table. So for example, copper, the most common one is copper 2+, since it's the first one listed on the periodic table. So we would go copper 2, and then oxygen is oxide. Okay. So that one's just multivalent metals. Page 9 is just polyatomic ions. So they have a spot for you to put the ions if you want, writing out the actual formula, and then the name. The third example is on those hydrates. So these are new. So make sure you try this page. We name the first part just regularly, and then you add the prefixes for how many waters you have, and then hydrate. And I would say number 11 is the most important one to try because it's mixed. So it has all the different types, and so it's a little bit harder if they're all mixed than just doing one type of ionic compound. So make sure you guys give this one a try for sure, and we will go over this the next day. Okay? And we will talk to you later. Goodbye.